All right, so chapter 8, fission and fusion. Yes. So we are going to talk about the first two scientists in the book really, really quickly. The first one is Ernest Rutherford. He was actually the person who discovered the nucleus. Okay, that's what he's known for. He bombarded nitrogen with an alpha particle. What's an alpha particle again? Alpha.
Oh, helium.
Helium, right? So he took a nitrogen atom and a helium and he slammed them together. I know it's a little fuzzy, but that's all I could do. He slammed them together and he discovered that when he did this, he produced oxygen. That doesn't make a whole lot of sense. So from this, he was able to kind of discover the nucleus, and then it was really small and it was really dense, and then it was positively charged. It was a much bigger experiment than that. He actually threw them at gold foil, and he was able to determine they were small and dense. And he actually, some of them ended up bouncing back at him, which he thought weird, because he said it would be like throwing a atom bomb at a piece of tissue paper and it bounced back and hit you. That's not going to happen, right? If you throw a bomb at a tissue paper, what do you think's going to happen? It's going to go right through, but what ended up happening is things bounced back. And so that's how he was able to discover the nucleus. All right, the next scientist that we're going to talk about really briefly is James Chadwick. He was the one who discovered the neutron. Rutherford was the nucleus. Chadwick was the neutron. What he determined was he could take an alpha particle and beryllium, and in the end, he could end up with carbon and a neutron. Okay, at first, before he came around to this experiment, they thought that a neutron was actually a gamma particle. Because if you think about it, neutrons are neutral. So are they going to be attracted to those plates we were talking about last week? No, they're going to pass straight through. Are gamma particles attracted to a side of the plate? No, they go straight through. And if you think about how the size of a neutron is really, really, really tiny, correct? So if it's really, really tiny and we can't see it and it's not attracted to either plate, it's a good assumption that maybe a gamma and a neutron are the same thing. But what they ended up noticing was that these neutrons would actually knock protons out of an atom. Well, if you think about it, gamma rays are not matter. They're just energy. So you can't move a cue ball unless you hit it with another cue ball, correct? So the only way that we could move protons is if something else had mass and was moving it as well. So they were able to discover the neutron. All right, so now skipping. Yes.
We were going to talk about it.
He skipped the first page and I had it highlighted.
I'm actually not really sure where these two definitions are.
We're going to talk about Albert.
Oh.
What? We're not going to talk about Albert Einstein?
Oh, see, that's why I didn't have it.
Well, I'm highlighting his name because I like him.
Go for it.
Because I like him.
Okay, anyhow, a few terms that are used throughout this, and again, like I said, I'm skipping a lot of history because I want to focus on the science. There's a lot of scientists involved in the discovery. There's a lot of World War I talk, and there's a lot of Nazi talk, and there's a lot of secretive code words that they had to do to make these discoveries, and we're just going to focus on the science, okay? So, again, I said I don't know. What page is that on?
116 is the moderator.
116 is the moderator.
17.
And then 117 starts nuclear fission. So a moderator is a material which slows down neutrons, and this is very important in a nuclear reactor. Once you start a nuclear reaction, you can't stop it. Okay, once you start a reaction, you can't stop it. So the only way to stop it is to possibly slow it down. If we can slow it down and slow it down and slow it down and slow it down, maybe just like we can't technically half-life all of our atoms, eventually it's going to happen though. If we just continue to slow it down, maybe it'll eventually not have any more neutrons to create new reactions. Okay, nuclear fission. 117, right? Okay, this is the process of breaking a large atom into two smaller atoms. Okay, this is the one that is feared This is the one that we do in nuclear power plants. This is the one that gets all the bad stigma because this type of reactions cause a chain reaction. Once a chain reaction starts, again, there's nothing we can do to stop it. Okay? So Chernobyl blew up, right? Why do you think Chernobyl blew up? A chain reaction was started, and there was some human error at fault. There was actually a faulty something in the machinery that messed up, and then the person on duty who was supposed to catch the machine messing up didn't catch the machine messing up, and so then the reaction just started going more and more and more, and then at one point in time, no matter how many moderators they put into it, they could not stop the reaction because it was too far gone. So then it just blew up. All right, so this leads us to something called a chain reaction, which is kind of what I was just talking about, which is continuing from 117, I believe.
I don't think it's highlighted.
Okay.
Why is there yellow on my page? But that was mine too.
Okay, uranium is very, very, very large. It has a lot of neutrons, and it is a very radioactive atom. What do I mean when I say an atom is very radioactive?
It has a very short half-life.
It's very unstable, and it's going to decay into other atoms relatively quickly compared to if we're talking about its half-life. Its half-life is going to be in maybe seconds or minutes versus years. Okay? Therefore, when it goes through a radioactive decay, it is greatly possible for excess neutrons to be released. So basically what's going to happen is let's just go with uranium. Uranium is what we do fission with most likely. That's what nuclear power plants do. So let's just go ahead and start talking about uranium. We're going to take uranium and we're going to go through fission. So uranium is going to break apart into two smaller nuclei. But in the process, since he is so neutron rich, he is going to not only break apart into two smaller nuclei, but he is going to release more neutrons. Those more neutrons are then going to go hit more uranium atoms, causing them to break apart into two smaller atoms, releasing neutrons. So you start with one reaction, and maybe it releases two extra neutrons. Well, those two neutrons can go hit two more uraniums, and then those two uraniums each produce two neutrons, so now we have four. And those four atoms are now going to produce two, so now we have 8. And so you can see how this process is going to grow exponentially, right? 8 turns into 16, turns into so on and so forth, going on, so right? So it's just going to continue exponentially. So if you're not paying attention, like I said, the half-life of uranium is probably seconds to minutes. If you're not paying attention for 10 minutes, this chain reaction could be too far gone, right? Okay. So here's a picture of what's happening. We have turn on my pad. Okay, so here's our uranium. It's smack dab in the middle. Okay, and in order for this reaction to kind of speed up, uranium would naturally decay into two smaller things if it wanted to. This picture's on your book. I found it on the internet. But in order for this reaction to maybe happen a little bit faster so we can control it just a little bit, we need a neutron. Yes, it would decay on its own, but to make it happen a little faster, if you hit it with a neutron, it's going to cause it to be even more unstable and cause it to break apart. When it breaks apart, it's going to form two elements, not always the same elements, but in this case, it's going to form krypton and barium, and in the process, it's releasing 1, 2, 3 neutrons. What do you think those 3 neutrons are going to do? They're going to go hit another uranium, 3 more uraniums. Each one of those uraniums is then going to produce what? 3 neutrons. Those 3 neutrons from each uranium are going to go hit more uraniums, and those uraniums are going to break apart and form neutrons, and it just continues and continues and continues. Okay? Fission involves the breaking apart of a large nucleus when struck by a neutron. Now again, uranium can do this on its own, but the neutron just makes it speed up a little bit faster. Some atoms fission more easier than others. Some of them are more unstable. Some of them are more stable. It just depends on what element you're dealing with. Uranium-235 will fission much easier than uranium-238. So if we're trying to figure out which one's more stable, Which do you think it's going to be? 235 or 238? Okay, 235 will go through fission better. So remember, the whole reason you go through fission is because you're unstable. So if 238 doesn't really want to go through fission, which it's more stable. So uranium-238 is more stable, therefore it's not as likely to go through a radioactive process. Will it? Yes, but not as likely as fission-235. Every time we create anywhere from 2 to 5. Not every reaction is the same. It depends on what your smaller atoms are. It depends on the surroundings, but you'll get at least 2 neutrons up to 5. Okay, during fission, more neutrons are released. This causes your chain reactions that I've been explaining. Okay, the products, which can be called fission fragments, are also highly radioactive. So in the example I just did, we talked about creating krypton and barium. These guys are usually also radioactive, which means they are unstable. So they will most likely try to go on and do another radioactive process. It's just, again, a chain reaction in every direction possible. All right. So, the next thing we're going to talk about is radioactive fallout. If I can get my... Okay, radioactive fallout. This is when large atoms can maintain more neutrons than small atoms. So, for instance, it kind of makes sense. Lithium only has 4 neutrons. Why? Because he only has 3 protons. It can only handle that much. Uranium has 238 minus 92. Has 146 neutrons. So depending on the size of your atom, you can hold more and more neutrons. And honestly, you need more and more neutrons. If you remember a couple weeks ago, we talked about neutrons, and they kind of act as the buffers between all the positive charges. If you put a whole bunch of positive charges in one room, they're all repelling each other. The neutrons act as buffers. The more protons you have in a small room, the more neutrons you're actually going to need to act as buffers. Okay? These fission fragments, just like radioactive processes, are not all the same. Okay? Some of these have really short half-lives, which means they're bad, right? Some of them have really long half-life, which means they're not going to cause a whole lot of damage, but it's going to take them forever to be safe, correct? Okay, in a nuclear explosion, they spread out everywhere, and we cannot control it. When we dropped the bomb on Japan, we just threw it down on the ground, and it was not contained, it was not controlled, the radiation went everywhere. So the actual nuclear fission was only the beginning, right? It caused this massive chain reaction. It caused all of this radioactive waste, for a better word, everywhere. And so people, I mean, who knows, it's probably still not 100% over. There's probably still seeing side effects of it now. Okay? There's just no way to really tell what the damage is. In a nuclear reactor, we can contain it. Nuclear reactors are usually contained. Remember when we talked about the rays, we talked about we needing 6 feet of lead and concrete. So usually nuclear reactors are encased in concrete and lead to try to contain the radiation as best as possible. The only way the radiation is released is if it goes poof and explodes and breaks through the concrete and the lead. Okay? What makes radioactive fallout is bad is when we come into contact with isotopes that our body can store. Okay, so like for instance, iodine. Iodine is stored in your thyroid. It controls your metabolism. That's the only part of your body that uses iodine. So if you ingest an iodine isotope that's radioactive, thyroid cancer, basically. Your thyroid is not going to act properly anymore, and that's going to affect a lot of your body systems. Okay, another one is strontium, which is number 38. Strontium is very similar to calcium, isn't he? Remember when we talked about the periodic table? He's in the same column, which means he's going to form the same type of ion. He's going to do the same type of chemical reactions. Don't you need calcium? What do you need calcium for? Your bones. So if you ingest some radioactive strontium and it starts to replace the calcium in your bones, well, as it starts to decay, it's going to start a chain reaction in the cells in your bone. And again, this can affect your bone marrow. This can cause cancer such as leukemia. so on and so forth. So again, it just all depends on the context of the radiation you're exposed to. Okay, in order for fission to take place, we need several items. The first one, of course, is the easiest. We need a fissionable material. We need something that will go through the process of fission. And honestly, there's only two main ones that will go through this process. This is uranium-235 and plutonium-239. And these are actually not the common forms. The most common form of uranium is uranium-238. Uranium-235 exists at most in 1%. 1% of all the uranium is uranium-235. Okay? And I'm not sure of plutonium off the top of my head, but I'm sure it's a small percentage as well. Most uranium we come into contact with will not do fission properly. Okay, the second thing we need in order to get fission to take place is we need a supercritical mass. What this means is we need a product that uses efficient neutron capture so that fission, I think it's supposed to be replaced, so that fission will happen faster than the capture, leading to more fission. So basically what that means is, like I just said with the chain reaction, in order for fission to happen, the fission has to happen faster than the neutron capture. Because if we're capturing all the neutrons, then we have nothing to cause the reactions. So we have to somehow get it to where the fission is happening faster than somebody stealing all the neutrons. So if we want to slow down a chain reaction, we need to put something in there that's going to steal neutrons. Okay, that's what a critical mass is. Critical mass means it's happening at the same rate. So your reaction is stable, it's happening, you're producing energy, yay, but at the same time you're controlling it. The opposite of that is a subcritical mass. That's when neutrons are being stolen faster than the fission reaction, so basically it looks like not a whole lot's happening. The third thing that you need in order for fission to take place is a source of neutrons. If you don't have neutrons, fission is most likely not going to happen. Now again, uranium will go through the fission process very slowly, but in order to kickstart it, you need a neutron. All you need is one tiny neutron, causes the chain reaction to start happening. Okay, usually it's called an alpha emitter, and we use an alpha particle to start the chain reaction. All right, so this supercritical mass that we've been talking about. Supercritical mass was the second thing. This is when we need fission to happen faster than our neutrons are being stolen. Okay, there are two types that we can do this. Okay, and this is honestly two types of bombs that we have. We're talking about atom bombs. Okay, this is how they control it, because if you have an atom bomb, you don't really want the reaction to take place until you're far enough away, correct? So there are two types. The first type is a gun type, and it sounds exactly like it, or it is exactly what it sounds. You put your two subcritical masses at opposite ends of a tube. And then when you're ready for the reaction to happen, one side gets slammed into the other side. And in the process, it's like all the neutrons are going to get messed up. And they're hoping that if they slam them together, a neutron's going to fly loose. All it takes is one little neutron to fly loose. And then it starts a chain reaction for a atom bomb. All it needs is one tiny neutron. So if they have 5 grams of each, which honestly, think about how many atoms that must be. 5 grams of each, they slam them together, the chances of one neutron is probably 99%. Okay? The other type is an implosion type, and that, you guys, everyone knows what implode means, right? Implode is when it kind of comes within itself. So what they do is they take your sample, and it's stable because there's no neutrons, and what they do is they just squeeze it from every direction. So it's like if you were able to take it, like if you take a balloon and squeeze it, it starts to pop out through your fingers, correct? But if you have 1,000 fingers and can get every single inch of the balloon, technically it's just going to compress and compress and compress and compress because it's a gas. It can keep compressing. Well, eventually, if you keep compressing atoms, they should start to try to mix together. When they try to mix together and their nucleuses start to combine, you're going to release a neutron somewhere and it's going to start the chain reaction. Alright, so that's fission. Fission, you take one big guy, you break it up into 2 smaller guys, you release some neutrons along the way, which cause a chain reaction, correct? That's all fission is. The next thing we're going to talk about is fusion. This is the opposite. You take two small nuclei and you squeeze them together to make a bigger nucleus. All you need to do fusion is hydrogen. You take one hydrogen plus another hydrogen and you form helium. This is a fusion process. Okay? In fusion, you move from a less stable nucleus to a more stable one, and this is what the sun does. This is how the sun works. Okay, so we take one hydrogen, we slam them together, and we get another hydrogen because we're not quite there yet. Then we take another hydrogen, slam it together, and oh, we finally get helium. Okay, so this doesn't always happen in one fell swoop. Sometimes we have to do a little bit of exchange and make some isotopes along the way, which is what happened right here. Over here, we have a hydrogen and a hydrogen. They're slamming together to form helium. And in the process, what do you think this light is that you're seeing all over the place? Energy in the form of what type of radiation? Gamma rays. Okay, so it's releasing a whole lot of energy, which is exactly what doesn't the sun release a whole lot of energy? Every single time hydrogen and hydrogen are fusing together to form helium, we see a little bit of light. So how fast do you think that's happening on the sun? A lot. Think about how many atoms that must take. And not only that, but think about how massive the sun must be to maintain this type of reaction for as long as it's been going. And for not only that, for how long it's going to continue to go. Okay, something that fission and fusion have in common. Okay, first of all, both forms result in a release of energy. Both forms release energy. Some in the form of gamma rays, some in the form of radioactive materials. Okay, but the big part about fission and fusion, the whole point atoms go through these processes is to try to form a more stable nucleus. That is the whole entire point. What page is that on in the book? Someone's underlining it. 131. For those of you who are underlining, on page 131, it talks about this main point right here, that they are trying to move from a less stable nucleus to a more stable one. I would star that, circle it, underline it, highlight it, whatever you're doing, because that is the whole point of fission and fusion. You are trying to make a more stable nuclei. Okay, so we have fusion on the sun. Do we have fusion on Earth? A much different form, because if we tried to recreate fusion like we have on the sun, that would be bad, right? So we have a much smaller form. Honestly, what we do on Earth is we use the heavier isotopes of hydrogen. So we use hydrogen 2 and hydrogen 3. And this is honestly how we make hydrogen bombs. Hydrogen bombs are bad as well, correct? Okay, to achieve the high temperatures, because if you think about how hot the sun is, that is the temperature required to make two hydrogens form a helium. So the only way we can even remotely get fusion to happen on Earth is if we first start with the fission reaction. So we need a fission reaction to produce a whole lot of energy really, 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 really fast, raise the temperature. Once the temperature gets up to a really high temperature, it will then fuse hydrogen into helium. But do you think we can maintain this process very well? No. Why can't we maintain this process very fast or very long? Okay, think about how big the sun is compared to Earth. Okay, think about how much mass the sun must have in order to maintain fusion. Our planet is not even that big. Not only is our planet not that big, but the amount of mass we would need to maintain that type of reaction is so far beyond what we can possibly have or afford or create that it's just impossible to make fusion last for more than just 30 seconds or so, however long it takes a bomb to explode. Alright, so then we have residual radiation. If the bomb detonates close to the surface, then the dust and debris is sucked into the mushroom cloud, which can then be spread relatively easily. Basically, all you need is a gust of wind. Okay, so think about hydrogen bombs. We used hydrogen bombs in, was it World War II as well? I think so. Hydrogen bombs. All we had to do was detonate the hydrogen bomb and then let nature take its course. Rain, falling down. It would cause the water to then be radioactive. The wind would blow it, the dust and debris, to other areas that maybe weren't initially affected, but then the wind brought it there, and so then those people are coming under the same effects. So again, no matter what we do, when we're doing some sort of nuclear warfare, it's bad because you can't control it. There's too many factors. So, homework, page 133, numbers 1 through 17. This is very brief. I strongly suggest you, at the very least, skim this chapter. Okay, now, like I said, he kind of gets off into the history and he starts talking about Mussolini and the Nazis and all that stuff. So I would skim through it, though, and try to hit the highlights of the scientific discoveries, okay? All right. Have a good night.